Hi, my name is Kiran, and I'm here to present our paper, Automating Mechanism Design with Program Synthesis. In mechanism design, there are self-interested agents that act autonomously and learn to use the mechanism to achieve their own goals. Now we ask the question, how can we incentivize these self-interested agents to maximize a global objective, such as revenue in an auction, or efficiency in a traffic intersection, or social welfare in economic production? Recent approaches for mechanism design cast it as an optimization problem over some parameters such as the proportions in which a resource is allocated to different agents, which is then solved automatically. And the main reason this is done is to avoid the limitations of manual or algorithmic mechanism design, which is not scalable to complex situations and requires simplifications and idealizations. And further, it reduces the burden on the designer. Many of these approaches use machine learning where the mechanisms are expressed as models. For example, a classifier that decides who wins an auction. These models are learned using usual gradient-based techniques, including deep reinforcement learning. These approaches have the advantage of being scalable and allow for flexibility in objectives and behavioral assumptions. However, there are also some issues. Uh, First is of interpretability. The mechanisms that we design often have human stakeholders and they need to be able to inspect and analyze them. This is not feasible with powerful models such as neural networks. The second is that we would like to be able to utilize prior knowledge as much as possible about what the structure or behavior of the mechanism should be. With ML models, it is not easy to specify such prior knowledge or to ensure that the mechanism is consistent with it. The solution we propose is program synthesis, which in general aims to automatically generate programs according to some criterion such as maximizing performance or satisfying some declarative specification. In program synthesis, there is a search space of programs in a domain-specific language or DSL, which is a small programming language specific to the application. For mechanism design, we search for programs in a DSL that represents the mechanisms that we seek. Program synthesis addresses the two issues we discussed. The first, programs are human interpretable and can be read and understood by humans. Second, by appropriately choosing the DSL, programs allow us to directly incorporate prior knowledge. We now give a brief overview of the multi-agent environment formalism that we use. We use Markov games which can have many agents. There is a joint state space and each agent has its own action space, a reward function, and a strategy or a policy that it follows. We call a set of strategies that the agents follow a strategy profile, and a trajectory is a sequence of states, actions, and rewards resulting from the agents executing a particular strategy profile. Now we present our program synthesis formulation of mechanism design. There are three components in the formulation which we now discuss. The first is the search space, which is a space of admissible multi-agent environments represented by programs. And next is the behavior generator, which for a given mechanism defines the distribution of possible agent behaviors that could result from that mechanism. Possible choices include game theoretic solution concepts such as Nash equilibria or learning algorithms, particularly multi-agent reinforcement learning algorithms. Finally, we have the objective function, which evaluates an environment under given behaviors. As we saw earlier, this could be something like revenue, social welfare, or efficiency. Putting it all together, we pose the programmatic mechanism design problem as the question of finding a suitable programmatic mechanism from a search space that, under certain assumptions about agent behavior, lead to outcomes that maximize a given objective. Let us look at a concrete instance of our problem framework in a traffic management domain. Here, two agents need to cross an intersection to get to their destinations. At each time step, the agents can either move one square or stop. If the agents meet at the intersection, there's a 2.5% chance that they collide. Regardless of whether they collided, they can continue onwards. Uh, the mechanism design goal informally is to come up with a set of signals and traffic rules for agents to follow so that they have safe and fair passage across the intersection. Formally, the search space for the problem has programs that decide the next states of the signals given the current states and whether to penalize each agent for breaking the rules. And the DSL consists of 4 tuples of Boolean formulas that are also given 2 additional inputs indicating whether each agent crossed into the intersection. The formulas could have up to 2 binary AND or OR operators. For the behavior generator, we use multi-agent RL to model agents learning to take the best possible actions to reduce their travel time. The specific algorithm we use is independent Q learning, where each agent learns independently of others using Q learning updates. The objective function, which is averaged over episodes, is 0 for an episode if the agents meet at the intersection, which we consider unsafe, or an agent is not able to reach its destination without penalty. Otherwise, it is based on the difference in travel times of the agents, which means that the best mechanisms are the ones that ensure almost equal delays. We now present our approach for solving the programmatic mechanism design problem. We are only allowed to sample from the behavior generator and the objective function, and that is we cannot backpropagate or perform other analysis. And our approach also needs to be suitable for large combinatorial search spaces. Therefore, we use Markov chain Monte Carlo or MCMC as the basis of our approach. What this does is to generate a Markov chain of programs such that in steady state, better programs are more likely to appear. The algorithm starts with a random candidate program and repeats the following process. First, it uses a proposal distribution to randomly make small changes to the candidate. It then evaluates the rewritten program by running the behavior generator and the objective function using the learn behaviors. Finally, it decides whether or not to accept the candidate based on how much better it is and starts the process all over again. Since the above process can be slow to find good programs when numerical parameters are involved, we propose using Bayesian optimization to efficiently tune these parameters. Before the rewritten program is evaluated, the numerical parameters involved in the program are tuned to get the best performing parameters. We now apply our approach in experiments starting with the traffic domain that we discussed. We find several sensible mechanisms among the best performing ones that the approach finds. Particularly, we have the usual signals and rules that the agent must cross only when the signal is green, and another one that is the same except with the meanings of red and green interchanged. And now we experiment on a more complex domain, namely the hunt and gather domain. This is an economic domain where agents can move around, collect and trade resources, and build houses to earn coin. The abundance of the two resources can vary between episodes. Sometimes a resource is scarce and at other times it is abundant. In this domain, the aim is to design economic policies that decide two things. Taxes which can be high or low with predetermined tax schedules, and market prices for wood and stone at which the agents trade, which can take 3 levels. The DSL of programs here consists of decision lists, which are a sequence of if statements where an action is taken based on a condition. Programs take resource abundances as input and output the decisions that we saw above. For example, the program shown here raises the price of a resource if its abundance is less than a particular value. The behavior generator in this domain simply has the agents performing fixed roles in a supply chain where two of the agents collect resources, and a third buys them and builds houses using them. The objective function is based on utility. Agents get utility when they earn coins and lose utility when they perform labor such as gathering or building. We use equality of utility as a welfare metric, which is calculated as 1 minus the Gini index of the utilities experienced by the agent. We now benchmark our approach with and without Bayesian optimization for parameter tuning and compare it to a decision tree oracle that is trained using the CART algorithm. We find that it is able to quickly find programs that perform close to the oracle. Additionally, we see that the Bayesian optimization step dramatically speeds up the search. And last but not the least, we find that the programs we obtain are highly interpretable. Uh, it's easy to see that the best performing program shown here uh, raises the price of a resource when it's scarce, like the program that we saw earlier. For future work, we would like to improve the scalability of our approach. Uh, this is hard to do due to the two-level optimization problem that we face. Well, one idea is to leverage multi-agent RL for learning the mechanism as well as the agent's behaviors. For example, the recent AI economist treats the mechanism as just another agent in multi-agent RL. Uh, we can then apply well-known techniques to convert the learned mechanisms into programs. The other possible avenue is to use multitask or meta-learning to quickly learn behaviors for a given mechanism. Uh, Here, each program would be a task, and we could use an embedding of the program as task context input to the policy. Thanks for watching.